All right, so last time we were talking about recursion. And I made a point to say, like, recursion, students love to talk about how hard it is, but it's not trivial, but people need to stop saying that, oh, it's so hard, because it just scares people just learning about it off. And then they go in with the wrong attitude. No. It's just a different way of thinking about things here. I heard a boop. Any updates on the final exam? What about? What is there? It's going to be like 161s. That's all I got for you. Just. Oh, it'll be released the moment I'm allowed to, which is like I can't remember, but it'll basically be released the moment I'm allowed to, which is the very beginning of it's the very beginning of the exam period, and it'll be due. Do you think it'll be early exam period? No. Why? How long do we? Jesus. Same as last time. You'll have a week to get it done. I'm not allowed to give you anything longer. What do you mean, though, an early exam period? Like, why are you asking that question? I'm curious as to where that question's coming from. Oh, when we can start it. No, it'll be, whenever everyone else's exam period starts. All right. Yeah, so recursion. Now, if you could think of lists from Python or any linear linked structure that we've talked about, we can define this recursively actually in a rather natural way. So a list or a series of linked nodes is, I'll talk about this in reference to a list specifically, but it's true for a linked series of nodes. The base case of a list, here's another issue, an easy PR to fix. This should be an uppercase for consistency. The base case of a list is an empty list. There's a list with nothing in it. That is the base case of the list. And the recursive case is there is a head of the list followed by a tail that's a list. So consider the following list, A, B, C, D, E. This can be broken, this is not the base case, right? Because this is clearly not an empty list. But we can break this down into the head of the list, which is A, plus the remainder of the list, the tail of the list, which would be, everything except the A, B, C, D, E. And then we can do that again. We could take the B out, and then we're left with C, D, E. And then we can take the C out, and then we're left with D, E. Then we can take the D out, and then we're left with just a list with E. Then we take the E out, and then suddenly we're left with E, and then the remainder after a list of just E is, it's an empty list. So we can actually define these, like a structure like this, like a list, recursively as well. It's not just like the functions. It's the way we're storing data too, which is kind of cool. Okay, recursion. In counting example, it may feel like cheating to say 1 plus however many are after the front. In counting example, I feel like this can be grammatically improved as well. So another PR, just saying. In counting example, it may feel like cheating to say 1 plus however many are after the front. How many are after the front seems like we're skipping a step. So if I tell you, right at the very top, how many people are in this line? Well, there's 1 plus however many are after the front. This feels like a little bit cheating, right? Because it feels like I'm skipping a big part. You can't just say 1 plus however many are after the front, because however many are how many are after the front is another question that needs to be answered. But notice that in order to answer this question of how many are there in total, I need the answer to a subproblem, which is how many are after the front. And the answer to that will be dependent on a subproblem, and another subproblem, and another subproblem, and another subproblem, all the way until we're left with nothing. So it's kind of interesting that we are answering these questions by creating another question, but the other question is like a smaller version of the bigger question. So with the list example, we also saw that we repeatedly apply the same rule over and over again on smaller and smaller lists until we get the end, the empty list. This pattern arises a lot with recursion, repeatedly applying the same rules on slightly different versions of the problem, right? So how many people are there? 1 plus however many is left after the front. Okay, do that again, do that again. So we're repeating the same rule, the same question on a slightly different version of the problem. So as mentioned earlier, we're typically going to have a base case and a recursive case, and at least one recursive case, and at least one base case. There could be multiple. And we'll see an example of this when using trees a little later. Now, the set of natural numbers n can be recursively defined as, well, 0 is a natural number, and a natural number is a natural number is 0, or a natural number plus 1 is also a natural number. Now, with this recursive definition, we have a complete definition of the natural numbers. And for those of you that don't remember, the natural numbers are 0, 1, 2, 3, 4, 5, 6, 7, and so on. So with this definition, we have a complete definition of the natural numbers, which is great. With only like 2 little statements there, which is pretty cool. But it's kind of neat because sometimes with recursion, we can start at the beginning and just grow. Because like this right here, if I were to like make this in code to print out all the natural numbers, this would be like an infinite loop, right? Because, okay, 0, and then 1, and then 2, and then 3, and it'll go on for infinity. So it's an infinite loop, but that's okay because it's like the infinity is a part of what natural numbers are. So it's kind of neat that, I don't know, we're like, the base case is 0 is a natural number, and then we're working up from there to just grow. So we could start at the base case and repeatedly apply the recursive case to generate all natural numbers. And this is a great way to mathematically define something infinite. Though your computers will not be happy running this because you'll get a stack overflow because you'll have a stack overflow. You made too many call frames to push on your system stack. But we could also take this definition and use it to answer questions by working down to the base case. So I talked about starting at the base case and going like up. But sometimes we have a question where it's like, well, is 4 a natural number? And so we are starting at the number 4 and we need to work down towards the base case to get an answer. And often when that happens is we get an answer to a subproblem, which allows us to answer a bigger problem to that, a bigger problem to that, and a bigger problem to that, and so on. So if I ask, is 4 a natural number? Well, I can go down by saying, is 3 a natural number plus 1? Sorry, is 3 plus 1 a natural number? Because if 3 is a natural number, 3 plus 1 is a natural number. And then if I take the 1 out of the 2, it's a matter of 2. Then it's a matter of 1 being a natural number, because then 1 plus 1 plus 1 plus 1 is a natural number. So is 0 plus 1 plus 1 plus 1 plus 1 a natural number? Well, we do know by the definition of the natural numbers, right here, this recursive one, is that 0 is a natural number. So 0 is a natural number. Therefore, 1 is a natural number because 0 plus 1 is a natural number. That's this one right here. Therefore, 2 is a natural number because that's the 1 plus 1. Therefore, 3 is a natural number. That's the 2 plus 1. And then therefore, 4 is the natural number. That's 3 plus 1. So it's kind of neat. We started at not the base case. We worked our way down towards the base case by breaking the problem down into subproblems. In order to answer if 4 is a natural number, we need to know if 3 is a natural number. That's the subproblem. Then we need to know if 2 is a natural number. Then we need to know if 1's a natural number. Then we need to know if 0 is a natural number. It is. And if it is, I can then answer that 1 is. And if 1 is, that means 2 is. And if 2 is, that means 3 is. And if 3 is, that means 4 is. So we worked down and then back up. So with the original way, we started at the base case and just go up infinitely. But now we're starting with a specific question, and I'm working down by asking sub-questions, like subproblems, And then I work my way up by answering each of those all the way back up to the top. Now, what's kind of neat here, though, is let's say I just figured this out, right? I ask you, okay, is 4 a natural number? And you're like, okay, well, if 4 a natural number, well, I need to know if 3 is, and then I need to know if 2 is, and then 1, if 0 is, and 0 plus 1 is 1, and that's a nat. Instead of doing all that, what if I asked you if 5 is a natural number? Well, we've just established that 4 is a natural number. Isn't it kind of neat that any number bigger than 4, if I'm asking it if it's a natural number, any number bigger than 4, pick any number in your head bigger than 4. If you were to follow this recursive process to answer if that question is a natural number, like if I pick the number 4,017,000,017, because that's bigger than 4, in order to answer that question, I need to know if 4 is also a natural number. Because 4 being a natural number is one of the subproblems to the bigger problem. In order to know if 10 bajillion is a natural number, I need to know if 10 bajillion minus 1 is a natural number. 10 bajillion minus 2 is a natural number. I need to know if every number coming before it is a natural number, which is the pattern I just did. I took the 1 away. I took the 1 away. I took the 1 away. That's what this is. Factorial, recursive programming. What? I feel like this is also a bug. This shouldn't be there. I heard a boop. You say pick any number. Can I pick decimal? Well, no, because that's not a natural number. We're talking about natural numbers right now. Here's another bug. We've got this floating section that shouldn't be here because it starts here. So, programming recursively. So a factorial, if we write this with math syntax, it's like we use the exclamation point. So the factorial of a non-negative integer is the product of all non-negative between n and 1 inclusively. Numbers. This non-negative numbers between n and 1 inclusively. Man, there are a lot of issues in this page that could be PRs submitted for. Man, there's a lot of points people can make towards their Snickers in this one. The factorial of a non-negative integer is the product of all non-negative integers between n and 1 inclusively. It also includes 0, but this is addressed below. Okay. We can nicely define this. So this is n factorial. If I were to write this out, if I wanted to know what n factorial is, well, that's n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times times 3 times 2 times 1. Okay? But we define this mathematically, recursively as, well, n factorial. If n is 0, it's 1. If it's not, if n is greater than 0, well, then it's simply n times n minus 1. And so let's apply this. So if I were to say 5 factorial, is 5 equal to 0? No. Okay, so 5 factorial is equivalent to 5 times 5 minus 1. Well, that's 4. So this is equivalent to 5 times 4 factorial. Mind the fact that we've got the factorial part here. So here, let's draw this out. If I can find my little pen thing. So if I say 5 factorial, oh, is this not plugged in? It's not plugged in. Okay. If I were to ask what 5 factorial is, let's not worry about you right now. My goodness. 5 factorial. Well, we saw the definition. N factorial is equal to, forgive my terrible, is equal to 1 if n equals 0. I know this is ugly, just bear with me. Otherwise, it's n times n minus 1 factorial otherwise. So is n, oh God, this is so bad. I'm going to try to fix this real quick. If n equals 0. Okay. Well, 5 factorial is so now n is 5. Is n equal to 0? No. So it's equivalent to this part right here, which is 5 times 4 factorial, right? Because n is 5. 5 minus 1 is 4. And then we've got the factorial. So now we have this thing right here, but that's that subproblem. Is 4 equal to 0? No. So that means, well, 4 factorial, 5 factorial equals 5 times 4 factorial. 4 factorial equals 4 times 3 factorial. 3 factorial equals 3 times 2 factorial. 2 factorial equals 2 times 1 factorial. And for the simplicity here, I'm just going to say when n equals 1. We'll talk about 0 in a second. 0 is kind of funny. So we'll just stop it when n equals 1 just to be for simplicity. So see how, like, here, to answer 5's factorial, I got to know what 4 factorial is. And to know what 4 factorial is, I need to know what 3 factorial is. And to know what 3 factorial is, I need to know what 2 factorial is. And in order to know what 2 factorial is, I need to know what 1 factorial is. Blech. So I'm working my way down. But as I work my way back up, I go, okay, well, if 1 factorial is 1, so I'm losing track of my cursor here. No, okay. 1 factorial equals 1. That's a factorial. So if I know 1 factorial is 1, then I can answer, then I know this right here. That's just a 1. So 2 times 1, well, that's just 2. So we can replace all this with a 2. So 3 factorial is 3 times 2. Well, that's 6. So I could just replace the 3 factorial because 3 factorial is equal to 6. And then 4 factorial is 4 times 6. So that's what, 24. So I can replace all of this with 24. And then 5 times 24, that's 120, I think. So 5 factorial is 120. 120. Yay. But I had to work my way down, and then I had to work my way, back up. Because I needed to, in order to know 4 factorial, I needed to answer these subproblems. And then I could start answering the subproblems all the way back up. I find that pretty cool. So note, you will notice that 0 factorial equals 1. Oh, I hear a boop. This is cool. I agree. This is phenomenally interesting. You will notice that 0 factorial equals 1 and wonder why. Why do people say this is hard, though? I think people say it's hard because it's different and it requires you to kind of like switch a little bit. Are you about to get slammed? No. It just grows from this. But it requires you to kind of flip a switch in your head to go from the iterative to the recursive. But I think that's why people say it's hard, is because it's different. And I think a lot of people that learn programming before they get to like university, before they start learning computer science, I think it's not very common for people to know recursion. I think it's a lot more common for them to just be writing their loops and doing everything iteratively. So if you have any experience with it, this is throwing you like a big curveball that's just going to throw you off. And so I think that's why people are saying it's hard. I also think it's this like myth that has been perpetuated. Like I heard that it was hard, so I then tell people that it's hard, even though it's not hard. It's not trivial. I want to be very clear about that. If you're scratching your head and thinking, I don't think this is easy, you're right. It's not. It's not trivial, that's for sure. But it's not prohibitively difficult. And like any new topic we learn, recursion isn't different. It's going to take practice. It's going to take time to learn and become familiar with it. No one is going to be expecting you to be an expert right now. No one will do that. That's a ridiculous thing for me to do. So we're going to be using recursion a lot over the next bunch of sections. Searching, trees, binary search trees, linked binary search trees, and the sorting. All of these are going to be making use of recursion. So we're going to get a lot of experience, with recursion. Okay, so you'll notice that 0 factorial equals 1, and maybe you're wondering why, because that doesn't really make sense. I thought recursion was calling a function inside of itself. I don't really see how this translates. It's right here. Right here. N factorial is n times n minus 1 factorial. The factorial is defined inside of itself. Right there. Hopefully that helps. Now, recursion, if you're looking for it specifically in programming, I mean, we can write this. We can write recursion, the recursive factorial, pretty easy. I think I do in a moment. Yes, we'll get right there. We'll get right there. I just want to take my time to talk about 0 factorial equals 1 and be wondering, like, what the hell? Because if you're thinking like, well, shouldn't it be 0? Because if you're multiplying all the, like, right? Well, it's because it's 1 by definition. It is because we say so. It is because whoever invented factorial said when it's 1, or pardon me, when n is 0, it's 1. So by definition it is, so deal with it. But if you don't find this to be a satisfying answer, because I don't, it's because 1 is the multiplicative identity. And it's used as the result when multiplying no factors. So this is just like how adding nothing together results in 0, the additive identity. So if you say 1 plus 0, it doesn't alter the value at all. If you do something times 1, it doesn't alter the value at all. So it's a mechanism to just have no alteration. And it also aligns with the gamma function, which is a generalization of factorial. But we don't need to get into this because this is well outside the scope of what really matters right now. There's only one combination for 0 things. Yeah, okay, you could think of it that way too. That's a really great way to think of it. Yeah, that is a good one. Okay, so if I ask you what 4 factorial is, we can calculate it by applying the rules. All right, 4 factorial is 4 times 3 factorial. 3 factorial is 3, 0 factorial is 1. 1 factorial equals 1 times 0 factorial, which is equal to 1 times 1, which is equal to 1. This is just the same thing we just did, except I did it to 5. So here's an iterative factorial. Iterative factorial, it takes some integer n. I'm going to create a variable called factorial, start it at 1. And then I'm going to say I'll start I at 1 too, just for ease, and say, well, I is less than or equal to n. Factorial equals factorial times 1. And then once we're done this loop, we return whatever the factorial is. So for example, let's put 4 in. Okay, we started at 1. 1. Okay, 1 is less than 4. 1 equals, factorial is now 1 times 1. Factorial is now 1. Okay, great. I is now 2. 2 is less than 4. 2 is less than or equal to 4. Factorial equals 1 times 2, that's 2. I is now 3. 3 is less than or equal to 4, so factorial is equal to 2 times 3, which is 6. I is now 4. 4 is less than or equal to 4. Therefore, factorial is going to be 6 times 4, which is 24. I is now 5. 5 is not less than or equal to n, so we stop the loop, and then we return the result. So this is the iterative factorial. This is the recursive factorial. And I want you to take a moment and bask in the beauty of this function right here. This is magical, isn't it? Sure, this isn't overly complex, but look at this. Isn't this, oh, this is glorious. So we've got this recursive factorial. It takes an integer n, and I ask a question. Is n equal to 0? If it is, return 1. Otherwise, give me n times, well, the factorial of n minus 1. That's all. That's what we're doing. So if we were to draw this out like we did with this, the only real, wait, do I still have this? I have this open from last time. Don't save. The only difference between how I would draw this out if I were to draw this visually, it would be the same as this, except I would just replace these little exclamation points with the name of this function called recursive factorial. So let's plug in the 4. And I will open up Paint here. just to keep track of some values. Okay. Let's put in 4. Okay, everybody, tell me. Oh, before I work on that, let's hear the question. Why you can call the method inside the method. Yesterday, when you do the program, it crashed. It's because we have the base case. This is a great question. We have the base case, which is like the stopping point. That's the n equals 0. So watch what'll happen. N is 4. Great. Is n equal to 0? Is 4 equal to 0? No. So we skip that if statement and we just return 4 times, I'll call this rec of 3. Right? But see, I can't actually return a value from that line 5 there until I have evaluated what recursive factorial of n minus 1 is, of what recursive factorial of 3 is. So I call the function. Okay, great. So I call this function, but n is 3. So is 3 equal to 0? No. Okay, great. So that's 3 times rec of 2. And that's going to be 2 times rec of 1. And then I'm going to run out of room. 1 times rec of 0. Well, when n is 0, it's 1. Okay, great. So I return the 1. So I can start throwing the 1s back to the calling function, and then they can start returning their values because they have a value. Like when n is 1, I go in here, and then I evaluate recursive factorial of 0. I go in here, I calculate recursive factorial of 0. Well, that's 1 in this base case here. So we return 1. And now once this is finished, I know, oh, well, this is just 1. So that's 1 times 1. So I can now finally evaluate this whole expression, and I can return it to the calling function. Cool, right? Both the iterative and recursive functions do the same thing. But to me, okay, be honest with yourself. Which one has more like, I know this sounds like a weird thing to say, but which one has more like beauty to it? Like there's an elegance to one of these two, I think. One is just so clean. Where the other one, I'm creating a variable, assigning values. I've got a loop. I have to update the Here, it's just, that's it. Recursive. That's what I thought. Recursive, but I'd still weird out how it's calling itself with multiple return statements is yes. Because you can kind of think that, like, remember, we can compose methods. Like, if I have a method that's like, I'm trying to think of the best way to explain this. It's probably better I don't get into it because it might just throw people off more. But whenever we see a call like this, I can't actually finish executing line 5 until I have completely evaluated the result of recursive factorial of n minus 1. Once that's done and I have an answer, like once this gets evaluated to an actual value, I can multiply it with n and then return the value to the calling function. Whether it was another recursive call or the first one, like in the main method, which is pretty cool. If you were far enough from the base case, would you get a stack overflow? In the grand scheme of things, it's slower because it's 2n times versus n. I know it's really small, but it's important though. Oh, okay, I see what you're saying, because I don't think it is 2n. I think it's still linear because we're not doing any more total steps. It's just passing the value back up. Now, when your question is about Stack Overflow, so that's a great question. Let's go here, lecture stuff, lecture 1, public static, n. Okay, so let's write this up. If n equals 0, Turn 1. I think I have an extra. Oh, yeah. Oh, int. Else return n times. Come on, where's the button? There it is. Of n minus 1. Okay. So if I go here and call back of 4. If I run this, I better see 24 as the answer. 24. Now, the question was, what happens if I do like 10,000? Will this cause a Stack Overflow? Well, let's see what happens. Yeah, it does. So, there are physical limitations here in terms of how these systems are engineered. But I want to get the point across. Do not conflate computer science with programming. Do not conflate computer science with writing Java code. Do not conflate computer science with how these computers are engineered and designed to operate. Would you have guessed and checked to find? Would you have to guess and check to find the limit? There is a limit. Let's see. Java recursion depth limit. What is the maximum depth of Java? It depends on the amount of virtual memory allocated to the stack. Yeah. I tested on my system and didn't find any constant values. Sometimes Stack Overflow after 8,000. There is a number, and it's going to be dependent on how much memory Java gets allocated. But a lot of times it would be fine. But like if I do 100, we're going to be just fine. Right? What? That can't be right. What? Someone see what I'm missing? What? 101? What is going on here? Oh. I know what's happening. Who here knows what happens? No, the IDE didn't bug out. Devin kind of raises an interesting point. Too many digits. It's not a Stack Overflow. It was the integer can only get so big. So it's because 100 factorial is a big effing number. Times 10 to the 157. So that's why Java was just, the number of zeros and ones needed, like the zeros and ones kept getting bigger and bigger and bigger such that it just gets interpreted as that. In fact, it's kind of interesting that 20 gives me a negative number, and that's just a consequence of how integers work and how they're represented in binary with something called 2's complement, which you'll learn all about next year. So that's kind of interesting. That's funny. Haha. Okay, so like 10 factorial is going to be a big number. All right, that's a pretty big number. Okay. Okay. Can Java not do scientific notation? If you want numbers that big, you're going to need to use something like, so Java will do scientific notation, but you're going to see those, like here, let's change this to double. So at 20, did it bug? Let's see what happens if we run it at here. See. So because a double actually has more bytes allocated to it, it can represent bigger numbers. But we're still going to have an issue eventually. 64, let's see what happens with 100. Well, we're still good. 1,000. Infinity. Look, it just gave up. It's just like, whatever. It's too big. It was 1,000 we did, but 100 it worked. So yeah, it's because doubles have double the amount of bytes an array and an int has. Wait, so can you use this for... Wait, so can I use this for infinity? What? I'm not sure what you mean by that, though. This is lazy, because there is an answer to this question. It definitely isn't infinity, but it approaches infinity as far as Java's concerned. All right, I'm gonna get back to the content here. Like if we need something infinite times, could I do this? No. There's something called lazy evaluation that you'll learn about later. Now there was another question I saw though. In terms of computational complexity, the computational complexity of doing this recursive and iteratively is going to be the same. However, in practice, as a consequence of how these machines work, in practice, recursion can get very slow. And it's because every single time your program makes a function call, which every time this method is called, it can make another call to itself. So if n is 100, there'll be 100 function calls. Every single time there's a function call, there is overhead. There's an amount of like work that Java has to do to create the call frame, to store the values, put it on the system stack. There's some work being done that you don't have to do iteratively. But what's really cool, and Java's particularly good at this, or at least they used to be, maybe, I mean, they still will be, but maybe a lot of other programming languages have caught up. But Java was actually really good with recursion because the compilers, the things that turn your code into like the zeros and ones that are running, I mean, asterisks because this is Java and it's a little different, but the compiler, the thing that turns it into what your computer can run, has a lot of built-in optimizations. And if there's something your compiler can do, it will, even though the code will be recursive, it will actually turn it iterative for you. Okay, both the iterative recursion, okay, when considering the call stack, the stack will grow until it hits the base case, then each frame will return the product of the calling function. So recursive factorial 4, well, it'll go to 4 to 3 to 2 to 1 to 0, and then start returning the values to the calling methods. So observations. Notice how the call recursive factorial 4 would have made a call to recursive factorial 3. If I ever call this function again, but want to check recursive factorial 5, we would have to call recursive factorial 4 again. In other words, to know recursive factorial of x, we will be answering recursive factorial of x minus 1, x minus 2, all the way to 1 and 0. So you may, so it's, you might start to think like, well, maybe I should have some sort of like bookkeeping. Like if I ever calculate the factorial of 100, you know, it's a linear time operation, but maybe I should store that value. So that way, if I ever want to call factorial of 101, I can just check if factorial of 100 is already known. Then I can kind of cut out all that extra work. You may have also noticed the relationship between the stack ADT we discussed and the call stack. Oh, interesting, right? The stack and the call stack. Anything you do with iteration, you can do with recursion, and anything you do with recursion, you can do with iteration. However, just because you can doesn't mean you should. And then here we're talking about creating the call frames and pushing and popping them onto the system stack. In many programming languages, compilers will optimize certain types of recursive functions by translating them to iterative versions. I just said that. This does not mean, however, that one should not use recursion, as sometimes recursion implementations are elegant and easier for you to write. Simplicity of your code may be a trade-off. Remember, sometimes good enough is good enough. If you end up actually needing to improve performance later, then do it. There are a lot of correct solutions to a problem. Both of these are correct. But I'm willing to bet if I put in if this function name was meh and this variable name was meh, I'm willing to bet if I gave this method or this method to an experienced software engineer, they'd look at this one and immediately know what it is. They would recognize it. They would look, oh, it's recursion. It's a recursive, it's factorial. This recursive example, this recursive code for the factorial and the iterative one are both correct. And we know that in practice, the iterative one is faster, although, again, your compiler will make this just as fast. But there's also a lot of value in the simplicity and readability and understandability of your code. So it's not about just being correct. It's about being correct while also being cognizant of your code. And this right here is, it's beautiful, right? Chef kiss. It's so nice. Where this one, variable, we're updating its value. I hate doing that. For loops, return. This, oh, look at that. There's just two questions. Is it 0 or not? It's nice. Okay, Okay, warning. The computers we use are one type of computational system, and although recursion often ends up being slower than iteration on our computational system, this is due to how they operate. Recursion is not intrinsically a slower process within our universe when compared to iteration. What I mean by this is the process of executing a recursive thing is not slow in our universe compared to doing it iteratively. One is not faster than the other. It's just a different way of describing the processes. It's the features of these computational systems we use that are slowing it down. Technically you could have different architecture designed for everything. I mean, I've got cells in my body that are computing things that are doing their job based on a lot of recursive definitions of things. There are cells in your bodies doing their thing based on recursive principles. There's no for loop in there. So they're doing their thing. That's a computational system, like it or not. And I'm not being weird. Sometimes people get really picky about the word computer in computation. Something weird happened in the last 100 years. The word computer just means something that computes things. Something that can execute and do a process. But our words have now become, the computer for your typical layperson means these boxes that sit on these desks. That is one specific type of computer. There are computers everywhere. So the cells in your bodies, they are computers, like it or not. I'm not pushing the limits of that definition. There's no argument to be had. They are. And they're doing this thing recursively. They're doing their things recursively, which is phenomenal. Okay. Computational complexity. You might start to think, well, okay, see, with the for loops, I look at this and I know what the computational complexity is. I see, okay, to n. Oh, it's linear. Factorial, oh boy. It doesn't seem as straightforward. And that may feel like it off the start, but you just kind of have to flip the way you think about it. Here, I'm asking how many times does the code in this loop get executed? Because this is the bottleneck, right? How many times is this going to run? N. Oh, okay. How many times is this going to run? How many method calls to recursive factorial are going to happen? If I put in n, and then I see a recursive call to n minus 1, how many are there going to be? N. How do I know n? Because if I go from n minus 1, and I stop at 0, there's n. So this is just linear. It just becomes a matter of how many times is this function getting called? How many times is this work getting done? Okay, when analyzing iterative code, one of the tricks was to think about how many operations we need needed relative to an input size n, and how much the amount of work done scales as we change n. When looking at iterative factorial n, we see that a few constant time operations do not depend on n, but we see the loop running constant time running constant time work that runs n times in total. Therefore, it's linear. But when analyzing a recursive function, the idea is the same. How many operations will be needed relative to an input size n, and how much amount of work scales changes n. But when looking at the recursive one, we see there's constant time operations like this, whatever. And then a multiplication and times, but then we've got this part here, which is like the recursive call. I'm going all over the place. So we also see the recursive call, which means the code inside the function can run repeatedly. The question is, how many times will recursive factorial n get called? Well, if we call it on n, it calls once, n minus 1, 2, n minus 2, 3, ... 2, 1, 0. So therefore, recursive factorial is also linear. Now, not all recursive functions are going to be linear, however. And we're about to see one right now. I don't think we're going to be able to finish Fibonacci today. But Fibonacci, raise your hand if you've ever heard of Fibonacci numbers. It's a very interesting series. Okay, a bunch of people, cool. So Fibonacci numbers, if you're not familiar with the sequence, see if you can figure out how it's created. 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, 144, 233, 377, 6, 10, 987, 15, 90, and so on. I'll give you a hint. 0, 1, 0, 1, 1, 0, 1, 1, 2, 0, 1, 1, 2, 3. Yeah. I know you didn't figure it out. You just know what it is. I get it. It's the sum. The next number is the sum of the previous two numbers. So 0 plus 1 is 1. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3, well, that's the 5. 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34, and so on. It's a really interesting sequence of numbers that has a lot of importance, but we're just going to talk about it for the sake of recursion. So to generate the sequence, start with 0, 1. Then to get the subsequent numbers, add the preceding two together. Take a moment to think about how you would write this iteratively to generate these numbers. An example is below, but make sure you understand this. We won't really have time to go. We'll pick up here again on Friday, I guess. But here it is. Iterative Fibonacci, n. If n is 0, return 0. Otherwise, previous is 0, current is 1, and next is 0. Then we start I is 2. Okay. If I is less than or equal to n, next is previous plus current. Previous is current. Current is next. So this is just moving things down. And current is next is always the next number, but then once it's calculated, it becomes the current. And then once we're done everything, we return current. So this is an iterative Fibonacci. What is the computational complexity of this? If you look at this real quick, it's linear, order n. Why? Well, constant, but this isn't a loop that's going to run like n times. It's linear. And I mean, this function isn't too bad. There's nothing crazy complex taking place, but you want to see the recursive Fibonacci? Look at that. Look at that. Isn't that wonderful? Look at that. Which one looks more elegant to you? This one or this one? Oh, that's or. I feel like you should definitely know that by now. Raise your hand if you think, well, whatever, people are leaving, we're out of time. But obviously the recursive one looks so much nicer. It is gorge, I know. Yeah, I do love it too. Except you want to know a secret? It's a really terrible algorithm, but we're going to talk about that on Friday. It's actually, its computational complexity is absolutely horrible, and we'll talk about it. And it's because this algorithm and this algorithm are operating very differently. But we'll hit that next time. Anyways, we're out of time. It is pretty, though. It is.